Hello and welcome to today's Tech Talk on uncertainty, ML plus OR, and stochastic optimization, a Q&A with Nextmove and the Seeker Creator. Today's presenters are Carolyn Mooney, Ryan O'Neill, and Meinhof Selman, who are from the Nextmove team, and our featured guest today is from Inside Opt, the creator of Seeker. My name is Haley, and I'm part of the Nextmove team supporting today's event, so I will be behind the scenes helping out as needed. The bulk of our time today is going to be spent in the Q&A with a little bit of lead up and orientation, along with a speed run of Nextmove and Seeker working together. We encourage folks to ask questions or chat. Just be mindful as you're doing that in the chat area to keep an eye out for the everyone versus hosts and panelists toggle to make sure that your message gets to the right place. You're also welcome to use the Q&A feature down at the bottom of your screen. Bear with us. We'll make sure that we get those questions funneled through to everybody. And with that, I'm going to disappear into the Zoom backstage and hand it over to Ryan.
Thanks, Haley. And thank you, Meinhof, for joining us today. This is some really exciting technology that I am going to show you today and that we'll be talking about. So first, let's answer the question, what is Seeker? I don't want to steal Meinhof's wind, but just to sort of set the stage for the two pieces that we're going to be showing working together. Seeker is a new optimization solver that does both stochastic and deterministic optimization. We'll show it today in the context of stochastic, which is pretty exciting. It was developed by Dr. Meinhof Selman, who's the CEO of Inside Opt. It has an approachable, expressive Python API, which we'll be using and showing. And it has lots of different use cases. It's been used in things like train yarding, hydropower, price optimization, etc. Meinhof will get more into the backstory as we do Q&A. And what we'll be showing as our example today is a stochastic production planning problem. When we put these two technologies together, what you can see is us sort of going through this stargate of deployment, testing, and experimentation for stochastic optimization problems. And so what we'll look at in a minute in the speed run is like this very integrated, seamless experience where we can generate a lot of interesting data, look at the ability of a given model to react to change within an environment, and not have to do a lot of that sort of legwork to get that working ourselves. So when we add these two things together, what we can do is we can build stochastic models quickly or deterministic. We can deploy them to remote infrastructure. We can run tests like scenario tests, acceptance tests, shadow tests. I will show you the output of a scenario test today. And then we can integrate these things into CI/CD for sort of normal software development practices as applied to models. And all of that gives us the ability to get buy-in from stakeholders in what are typically uncertain environments in new and powerful ways. So with that out of the way, let's go over to our speed run. So the first thing we're going to look at here is our input file, and hopefully this allows you to understand the problem that we're solving today with Seeker. Again, we're doing a stochastic production problem. So we're pretending that we have a sushi restaurant and we are producing different kinds of sushi. Meinhof has a good video on this, which you can also watch about sort of how the nature of the problem and how stochastic optimization can help solve it. So here we have different products that we produce, which are things like chirashi bowls, sashimi boats, and sushi platters. And each of these things has a cost for production, which we lose if we produce something and nobody buys it, and then a profit if somebody actually does buy it. So I might make a chirashi bowl. If nobody wants it, I lose $4.32. But if somebody does buy it, then I net gain $3. And we have minimum and maximum production values for each of these products. Each product takes some sort of resource or combination of resources, and we have constraints on those resources. So for example, we have tuna, and a chirashi bowl takes 2 units of tuna, whereas a sashimi boat might take 5. And we have 10,000 total units of tuna. And the same with salmon, cucumber, razor clams, and rice. And all of these resources constrain the products that we can create, right? So we can't produce products when we don't have the resources for them. Finally, we have our forecast, and this is where things get really interesting. So you might say, in a typical production problem, we'd have a point estimate on the amount of demand that we're trying to meet. So I would produce, say, 300 units of X and 800 units of Y. But in the real world, we, of course, have uncertainty. And so what we're doing here is saying we have a point forecast, which is 300 units of terashi bowls, but there is noise around that point forecast. So we have here a normal distribution where we describe what the error is on that forecast. And we're going to use that directly in the model. So let's look at the code for the model itself. So first we have, this is Python using the Seeker APIs and the NextMove APIs. So the Seeker APIs are going to handle the optimization, modeling, and solving part of it, and the NextMove APIs are going to handle the deployment, data loading, and everything that goes around it. So here we have the NextMove APIs where we're pulling options out of the NextMove cloud or the command line environment, which do things like tell us how long the solver is allowed to run for, or what the resolution is that we want to pass to Seeker, which is sort of a way of thinking of how many scenarios, random scenarios, Seeker is going to sample. We also have things like how frequently to report on the best solution, what the scenario seed is for randomly generating those scenarios, and what the solver seed is for directing the search. And we load that along with all the data down here. Once we have our parameters and our input data, now we're going to construct the model. And so you can see here, we're setting up a Seeker environment. We are turning on stochastic parameters with resolution and speed settings that we get from the command line or NextMove cloud. And we're creating decision variables for each product. So for each product, a terashi bowl, sashimi boat, and so on, we have a variable here, which is how many units of that to create. And here's where the magic happens. So now what we're doing is creating a demand term, which is that point forecast. So, for example, 300 terashi bowls with a normal distribution around it. And Seeker is now going to sample from this normal distribution to sort of represent uncertainty in the problem. From that term, we also derive our sales and waste, and then finally our profit. And so our profit is essentially how much we're getting versus the costs that we pay for wasted resources or wasted products. And it aggregates those into the mean. So we are maximizing the expected return. Finally, we add our resource constraints. We can't make things if we don't have the resources for them. And we call Seeker to optimize and then get output. And so here we have on our solution output, how many of each product to make, what the expected demand is going to be for different scenarios, and sales and waste, as well as some metadata and statistics from Seeker. All right. So once we have that written, we can push it into the NextMove environment with a simple NextMove app push command. And this will push this into NextMove Cloud where we can run it and we can do scenario tests and lots of fun things like that. All right, we've pushed it. It is now live and it has an endpoint assigned to it so we could make requests to our application. Once we go over into NextMove Cloud, we can see that it has endpoints associated with it and API references. Let's look at a specific run. I'll just load this one that I've already done. And we can see here's some metadata about the run, how long it took, what kind of instance it ran on. This was running inside of a Lambda function. We can see statistics about the run, what was the value, how many constraints and how many evaluations did Seeker do, so on and so forth. We can see configuration that we passed to it. So I let it run for 30 seconds. I set the resolution to 25,000 and so on. We can retrieve the input. So this was a slightly larger version of that input where we also have things like yellowtail sashimi and tempura shrimp rolls. And we can get the result from it, which tells us how much of each product to make, what our expected demand, sales, and waste are. And then we can also get the logs from Seeker. So here we can see that Seeker is improving the solution over time and doing lots of different evaluations and whatnot. We can also run large-scale tests with things like scenario tests. So I'll bring up one that I've already run, which is here. And what we did here was create a bunch of different scenarios where we varied the number of resolutions, i.e. the number of scenarios that Seeker would pull out of its random distributions. And we gave it the same scenario seed. So what this essentially means is we are generating the same scenario and then trying to optimize it with different samples, different numbers of samples. And we get a pivot table output from all of these runs. And so I think this resulted in about 100 runs. And if I pull out some of these values from the pivot table, I can see they were getting different values and different estimates based on the number of scenarios. There's different levels of uncertainty there. I can also turn this into something like a line chart if I want here. All right, so that's the end of our demo. I will stop sharing.
Awesome. Thanks, Ryan. Fun to see Seeker and NextMove, together in action. I know you shared some background or brief background on Seeker before, so Meinhof, I'm going to turn it over to you. I would love to hear a little bit more detail about kind of like, how you decided to go develop Seeker, and more specifically, kind of where you think it has a lot of power.
So I've been a developer for 25 years. I've lived the MIB world forever, built 2 MIB solvers during my career, actually. And that means I'm keenly aware of all the limitations that the traditional software has. While we're talking about stochastic optimization today, in reality, when you optimize in a business context, you quickly hit the limits of what traditional OR software can do for you. Typically, a business doesn't have just one KPI that they want to optimize. There are multiple ones of them. And then you have to think of ways to integrate them into one hybrid KPI, or you have to constrain one and optimize the other, but you don't really have a tool that gives you a good trade-off between them. Same thing when you have anything nonlinear, non-convex, non-differentiable. You have real problems there. And then, of course, parallelism is always an issue. If the problems get hard, you would like to be able to throw compute at the problem. And traditional MIB solvers, as you know, don't really parallelize all too well. It's very, very hard to do that with any dual approach, really. And then, of course, stochastic optimization, with most real-world problems are actually coming with estimates where you just don't know the future you're actually optimizing for. And you're often finding that the provably optimal solution for the point estimated future actually lets the business down on the day of operation. And so we wanted to build a different kind of solver, and we had to jettison the whole duality for it. So we built a purely primal solver, provides no bounds whatsoever, doesn't bother trying to assess how good it is. It just out there to find the best possible plan it can in the time that you have for it.
Yeah, no, that makes a ton of sense. I think we hear a lot of times from more the business side of the house, right, that like optimality isn't necessarily the concern, right? Or like, sometimes the thing you're solving for isn't necessarily the business KPI, right? So, I think there can be some tension there. We've heard like a lot of people starting to focus on stochastic optimization. And I think maybe Ryan, you've seen this as well. Like we went to conferences recently, et cetera. What, like, if you could encapsulate kind of like, what do you think like a really solid definition of stochastic optimization is? What does it have to do with machine learning? How do you see it bringing other people into the space, particularly as we see more data scientists coming into our community?
Yes, I mean, you have to talk about data pipelines, right? So if we're talking about the value of information, really, we want to go from the original data and to money in the end. That is the objective, not the best precision and recall or RUC curve that you can provide. You want money at the end, and that means you need to effect better decisions, which is, of course, what we are there for in optimization, and also next move to effect that, right? So what is a stochastic optimization problem? It's literally every problem where you are planning for a future that you do not know 100% in advance. And now they're very different flavors. I mean, this can go from, I have this value, this input value that, as you've seen just here in the demand, is uncertain. I just don't know exactly how much of this stuff will actually be bought. And then you might do expected profit optimization, but you might also look at value at risk. You might look at conditional value at risk. So that's relatively simple. Then you can have robust optimization, where you have lots of different scenarios, and you want to have a solution that works across all of them. You can have the more pragmatic one where you go stochastic optimization, right? So this is a traditional term for stochastic optimization, where you say I have a distribution for everything, and now I'm taking a statistic for my outputs and try to optimize that. And then, of course, you can have two-stage or multi-stage stochastic optimization as well, all the way to policy learning. where actually what you're trying to learn is, okay, so I have to make the same decision over and over again. And kind of the end state in which I'm leaving my system is going to be the start state for tomorrow. So now the question is, what is actually a good ongoing policy to learn? And you can do all of them with the same API, essentially by realizing that you can solve all of these if you view them as a simulation optimization problem.
It's definitely like an interesting space. I think maybe we can make it a little bit more concrete for people. So maybe a question for both of you is, what are some prime use cases when you think about like stochastic optimization? Like where does your head go? I know we just saw like the production example with sushi platters, which made it really real. But like, what are some other examples and like that lend themselves well to this space?
Yes, so I mean, literally anything that you've seen in the traditional OR literature, right? So when you're talking TSP, who knows how long it actually takes to go from one client to the next tomorrow, right? I mean, this is UPS has to do vehicle routing problems, and they do not know what the traffic is going to be tomorrow, and yet they give time windows to their clients and whatnot, and you have to solve that. Think just recently I did hydropower optimization. You really do not know where it's going to rain. And what I didn't know is that these basins get emptied and refilled during the day. So it really matters how much rain is actually going to fall there. And it's very, very hard to forecast. You just don't know these things. Anything where you're setting prices at the same time, you do not really know 100% how they affect demand. Those are all good examples for it.
Yeah.
Yeah,
Do you
I
think there's like
some of the I was going to say some of the things that come to mind for me are from our experiences, Carolyn, where we would try to do things in like gig economy or shared economy work where we'd make offers to independent contractors through models, but there was risk of offer rejection, right? And so you'd be trying to make these sort of discrete choices on who to give an order or delivery to, but you had very sort of probabilistic, a lot of uncertainty as to whether things would get taken.
Yeah, no, that makes sense. Do you think there's more focus kind of in this space as data science has become more prevalent within businesses? So like obviously we have seen a rise in the last 5 to 10 years of like businesses having these data science programs, building more predictive models. And now they need to make decisions given those predictions. I think that's always something that we found challenging in places that we've worked in the past, Ryan, like, getting people to understand kind of like, okay, yes, this is the expected value, but like, what happens if I'm at my P90 or what happens if I'm at my P10, right? For demand. Do you think that that's kind of impacting some of the push towards stochastic optimization and really like kind of that ML plus OR landscape?
Yes, I mean it's probably the industry where you see it the most is supply chain. Which is also the largest client for us, interestingly. They have had a couple of hits, from COVID to what was it, Evergrande stuck in the Suez and the Panama Canal running dry, and now all the stuff happening around the Horn of Africa, right?
Yeah, strikes now. Yeah, I mean, there's a lot of stuff happening.
So people are keenly aware of the fact that they can't just ignore risk. And now the question is, how do you properly manage it? And this is actually what happens. I mean, if you've ever tried to deploy a real optimization problem, you know that your stakeholders do not know in the beginning what they want optimized. Right? They come with a problem. They say, I have to decide the following thing, and I do not really know how to do this. And the moment that you show them the result of such an optimization and you can show them the distribution of how their KPIs look like, they suddenly have other wishes. They will go like, I don't like this tail over here. Can we do that too? And yes, you can combine these things in Seeker. You can say, okay, let me measure what the probability is that this KPI hits a certain threshold, and then say, I want to optimize that at the same time as I'm optimizing my expected profit, for example, using the multi-objective optimization, right? So like this, the solver allows you to find a solution where, to the extent possible, of course, you're molding the probability distribution of your KPIs.
Yep. No, that makes a ton of sense. And I think that's how a lot of, business stakeholders that I've talked to in the past, like think about their systems, right? They're typically like willing to maybe take a cut in one metric, right? In order to preserve another, right? From a risk perspective, or like they really think about those aspects. Given that you're seeing kind of this like shift, like how should decision science OR teams and even data science teams like think about collaborating and kind of incorporating both ML and optimization kind of like in one flow. I think we had actually a question in the chat just about that, like how is that possible within Seeker, how is that possible within Nextmove, and how can I actually go like deploy these systems?
Right. I mean, that of course is the actual business question, right? So how do you make
Yep.
that operational? You can't just tell all the data scientists, please learn optimization, and you can't tell all the OR people, would you please also learn machine learning? That obviously doesn't fly. So the question is, how can you do that? And maybe the bigger question there is, why would you? Right. So what people currently look at, right? So people are aware of the fact that things don't run so well during the day of operation. But they think, okay, we did our due diligence. My data science team, the machine learners are awesome. They did their cross-validation performance. They've increased accuracy by 3% in the past year. It's awesome. This is the best that the data will ever give us. Beautiful. And then you shove over, so you lose all uncertainty. You just say, oh, these are my point forecast, and hand it over to the OR team. And the OR team comes back with a provably optimal solution. Yep. So, I mean, as an exec, you're sitting there and you go like, well, the rest is just the cost of not having the Delphi Oracle in the basement, right? Yeah. I just don't know the future, and this is just the cost of doing business. The point is, no, this is not the cost of doing business. The cost that you're seeing there, the mayhem that happens on the day of operation, is the result of you over-optimizing one predicted future. So it's the handoff that is the problem, and this is exactly what I think we've addressed reasonably well by saying, look, all that the machine learners do differently now is they don't provide point forecast. What they estimate is not the demand; they estimate the distribution of the demand.
Yep.
Right. So, and this is typically very easy. I mean, even if you're not using, I don't know, a Gaussian process to do that, which will give you the distribution for free, you can always use your cross-validation performance or something like that in order to make things distributed. And thereby also acknowledge that in certain times you have a much clearer idea what the demand is going to be than in others. So this can be a heteroscedastic forecast, right? Depending on what the features are, you might say, oh, today I have a lot of variance, and tomorrow you might say, no, I actually know that this is the way it is. You tell us over that. And all that the OR people need to do, well, all is said too much, maybe, is use Seeker, of course, right? So you just shove those distributions directly into the solver, let it know. And then you start having this iteration with the business stakeholders where they go, oh, this is what my distribution looks like. Beautiful. I don't just get a number that I don't believe, but what I'm getting is, hey, this is my risk that I will not be able to pay rent next month.
Yeah. I think like there's something interesting too, just in like the team dynamic that you kind of mentioned there, right? Where you can continue, and we've talked about this in the past, like continue to improve your input into the optimization over time. Now that input is just getting to the point where it's a distribution versus a single value, right? And so you can still have your data science teams, right, or your predictive teams, right, like working on those predictions over time and making them better and better, or as good as they can be for a given feature set. And then you have on the other side, you can continue to leverage, this like stochastic optimization framework, right, with Seeker, and you can really improve your decisions that way. So I think that's an interesting parallel path too, to like kind of separate concerns almost in like the decision-making system and the like input driven from those distributions. Ryan, I think you've been chatting with me a little bit about that in the past couple of weeks.
Yeah, one of the concepts that comes to mind is the concept of the knife's edge, where without uncertainty in the model, optimization is just very greedy, and it will optimize itself all the way onto this sort of very thin ridge where it will fall off once there's data that's not what it was expecting, right? And now that we're getting technologies where we can add that uncertainty in convenient ways to the optimization, it's not that the optimization is necessarily less greedy. It's just that it has more information and it can do something with that.
Yep. Yeah, no, that makes a lot of sense. Maybe a final question for you, Meinhof, and then we have a few questions that we want to get to. So, what is the best way to get started with Seeker and stochastic optimization? And are there any useful things to know when you're beginning that journey before we hop into questions?
So, I mean, we have a free collab on Google, so no installs required. You just go ahead and do it. Of course, the moment that you're actually getting closer to deployment, you should definitely talk to Nextmove and get it done that way. This is actually what we say as a default, because we are a software shop, right? So if people come to us and they say, "Hey, okay, but can you run it for us?" We say, "No, we won't, but we got the right folks to do it for you." It's actually, I mean, we have a YouTube channel, we have a newsletter on LinkedIn. Everybody on the call, please feel free to connect with me on LinkedIn. We'll probably not get through all the questions that you might have posted, but I'll be happy to answer those in private chats as well. And yeah, I mean, just try it out. It is very, very refreshing because the modeling is so different. It's like you really have to get out of this mindset of thinking about the dual all the time and think like a human again. Like the person who would actually have to make a decision. I was just modeling a fleet assignment problem for an airline just yesterday. It took an hour and a half. And the model is unlike anything you will have ever seen for fleet assignment. But the moment you have it, you're suddenly liberated to have any nonlinear and stochastic variation thereof, because obviously you don't know the demand for the different tickets. And what the revenue is going to be. So it's greatly liberating and actually quite refreshing if you only live the MIP world so far.
Makes sense. Well, I know we only have a few minutes left and we want to keep to our half-hour time. So let's dive into some questions. We got a few good ones in the chat. I think, Meinhof, you answered one of them in line. So we'll skip ahead on that. We did get one in. I think we maybe addressed a little bit of this, but can we train an ML model to learn the distribution and run optimization at the same time? So maybe both of you can answer.
Do you want me to go first? I can. So inside of the Nextmove context, yeah, you can fit models to things like scikit-learn or stats models, or using other ML tools, and you can use those then as inputs in an optimization. And so you can even do things like ensemble runs, where you do different types of models and then sort of save those models out. We're not explicitly like an ML ops tooling, but since we are decision ops, we have to have some functionality in that arena. The interesting thing about that is that sort of when you get into the decision ops part of this, the model itself is now data, and sort of that's how decision ops and ML ops are a little bit different.
Yeah.
So, I mean,
also how to interconnect.
What's cool about Seeker is, and we haven't shown that here, we wanted to keep the example easy, but you could, of course, solve the pricing and production planning at the same time. And of course, the prices would affect the demand. So what you can do in Seeker is you can actually, the very thing that you want to decide what the prices are would be the features that go into the machine learning model. And you can do that in Seeker. You can say, okay, look, here is my first set of decision variables is the prices for my product. And the second one is how much of each am I going to order or produce, and solve both at the same time. All that your machine learning model needs to be able to do is, given the features, produce me a new set of samples of the posterior distribution.
Yep, that makes sense. Yeah. We have another one here. In supply chain, we have solvers which plan 36 months into the future, and nobody cares about precision and demand probabilities in month 35. Can we still use Seeker to bring some quality in that a classical LP would not have?
Yes, I mean, the audacity, right? I mean, you're thinking about a network design problem, and then you realize it takes me, I don't know, 15 months, 18 months to stand up a new warehouse. And then I'm going to keep my warehouse for 4 or 5 years. So who am I to put anything into a MIP model that says these will be my transportation costs and those will be the demands from my clients? You have no idea, right? So now the real question is, okay, so yes, I mean, you realize that, of course, the further out you go, you might have other options also to react, to kind of update your network, and you can model that. but more importantly, you can put higher variance on your forecasts in later years. And of course, you can discount them as well if you wanted to. So, if it's nonlinear, everything that you're sweating in mixed interval programming is not something to sweat anymore.
Yeah, no, that makes sense. Maybe one final question, and then I know we missed a few, but we will certainly follow up with folks, separately to make sure you get your answers. But we had a question: are there any toy examples we can play with? And so I think, Meinhof, you mentioned that there are in the Google Colab space. You could also bring any of those samples into the Next Move context as well. So you can push them up into Next Move and play with them there. But I think that's what you mentioned, right, Meinhof? And we can send a way to
Yes,
access
absolutely. And as always, connect with me on LinkedIn. I might have the one or the other collab that isn't official, and you can play with that as well. Yeah.
Sounds good.
All right, excellent. I'm coming back from backstage to wrap up today's session. So Meinhof, Carolyn, Ryan, thank you very much for your time today. Everybody for joining, thank you for your questions and all the engagement. As Carolyn mentioned, anything that we didn't get to live today, we will make sure to follow up with you afterwards. For those folks that are following along, we do have another Tech Talk coming up in a couple of weeks here about how to bring a custom Python decision model to Next Move, including things like Seeker, which is very exciting you saw today. And with that, we're going to sign off. So again, thank you everybody for joining. Until next time.
Thanks all. Thanks, Meinhof.
Thank you.